All right. So last time we ended up at the beginning of 10.2, where we have rotation with constant acceleration, which is essentially the beginnings of kinematics in rotational motion, right? So we looked at some of the kinematic equations and how they translate into rotational motion, and really it comes down to something really quite simple. And let's take a look at that simplicity. Let's see here. So in linear kinematics, we have things like x or y, or y. We have things like velocity. We have things like acceleration. Of course, we also have time. And in rotational, we have things like theta, omega, alpha, and time. And of course, you can see here that time and time are the same, right? Those two things are the same. These other things are different. So how do you go from one to the other? Well, you use these formulas. We have formulas like x equals r times theta, where r is the radius of the rotational motion. And we have things like v, the tangential velocity, or the velocity along the edge of a circle, is equal to r times omega, the angular velocity of that circle. And we have things like the tangential acceleration, the acceleration along the edge of the circle, equal to r times alpha. And of course, you can rearrange any of these equations and get three other equations. If you want to solve for theta, you get theta equals x over r. Or omega equals vt over r. Or alpha equals acceleration tangent over r. And of course, when you're dealing with things that are rolling, when they're rolling along a surface and there's no slipping going on, then the tangential acceleration is the same as the linear acceleration of the rolling object, right? And the tangential velocity is the same as the linear velocity of the rolling object. And the tangential distance, or the distance along the edge of the circle, is the same as the linear distance of the rolling object. So that's where the connection is when we're dealing with rolling things. Other things that we've dealt with so far are the kinematic equations. Well, you know, the kinematic equations, we have one that says velocity final equals velocity initial plus acceleration times time. Now remember, the kinematic equations are true as long as your acceleration is constant. So that is true here. And if we replace these velocities and accelerations with angular velocities and angular accelerations, we get a similar equation. Omega equals omega naught plus acceleration times time. Angular acceleration. And we have another one that says that's x or y equals x naught plus v naught t plus 1/2 at squared. Right? And over here we get theta final equals theta initial plus omega naught t plus 1/2 alpha t squared. And again, the t's are the same on each side, right? So if you're working with linear and rotational, like the string coming off of fishing reel or a wheel turning on a car or something where something rotational becomes something linear or vice versa, the t is always the same between them, linear and the rotational. And then there's also the relationships between them here. And we have also v final squared equals v initial squared plus 2 times a times the change in x, where change in x is x final minus x initial. And here we have a similar one, omega squared equals omega naught squared plus 2 alpha delta theta. So they're pretty much the same deal. When you're dealing with rotational kinematics, you can work with them just like you did linear kinematics. The only real big difference is that when we dealt with linear kinematics and we had 2 dimensions, we could create 2 sets of equations. With rotational kinematics, it's not so simple because we're not really dealing with in rotational, we're actually already in 2 dimensions, I guess is the best way to say this. Remember that rotational kinematics, rotational motion is a 2-dimensional thing anyway. You're dealing with it in a plane. So that's the only real difference. But as far as the math goes, it's the same math. You just have to set it up properly. So another example where the math of physics is the easy part. Many, many examples of that. So here are the kinematics of rotational motion, and they go through all the deriving of them just like we did in the previous sections. And I mean, it all comes out the same. There's no real difference. Here's a nice chart of the 4 different kinematic equations. And I actually didn't do the first one, the theta final equals theta initial plus omega t, or average omega t, whatever, but they're all the same. And so they use these equations to calculate different things. Now, oftentimes when you're dealing with these systems that are both linear and rotational, because something that is rotating becomes linear either through rolling motion or through something unwinding off of something circular into something linear, whatever. Oftentimes you can just choose whether you want to deal with the linear kinematics or the rotational kinematics. And then once you choose which one you're going to work with, you can just work with that one all the way through the problem and then just translate it into the rotational one if they want to know something about the rotational, right? Translate the answers over. So in this case, they give us the radius of this fishing reel. They give us the initial angular acceleration, and they give us the time. In this particular problem, they're actually going to do all their kinematics in rotational motion because they've given us all the numbers in rotational variables. So you might as well. And so they calculate the final angular velocity using initial angular velocity and time and angular acceleration. So the angular acceleration is the 110, the initial is 0, and the time is 2 seconds. They plug it in the equation, they get the answer. And then once they've got that answer, they can use that one in another one, but they don't actually do that. In this one, they actually they figure out how far this, the reel has rotated an angle, how many radians it has rotated by using this kinematic equation. It's not the only option. We could have used this final angular momentum or the final angular velocity in another kinematic equation to also figure it out. There you have multiple choices after you know a couple of things from the kinematic equations. But they use this one, and that's fine. They get the answer of 220 radians that it rotates through. And how many revolutions is that? Well, of course, there are 2 pi radians per revolution, so you divide the 220 radians by 2 pi radians, and you get about 35 revolutions that the reel rotates through during that time. And here they have an angular acceleration of negative 300 radians per second squared, and it's already spinning. So we already have this angular velocity. They're using this previous problem. And they want to know how long it's going to take to stop it with this angular acceleration, this negative angular acceleration. So they plug it into a kinematic equation, solve for t, and they're done. It's pretty simple stuff. Here they're showing the angular velocity of a propeller on an aircraft as a function of time, and just like with linear velocity, the slope of the velocity is the acceleration. So is this one speeding up or slowing down? What? Slowing down, but you can obviously see because in time the velocity is going down, but you can also see because the slope is negative, right? And they actually show that you can calculate that using an integral, because an integral calculates the area. Oh, here they're actually calculating. They're actually showing that the velocity, the angular velocity, integrated gives you the change in position, which would be the area under the curve here, which is fine. But here they're just calculating the slope as the change in velocity over the change in time. That's just simple. That's the derivative, of course. So anyway, they're just showing you all the same things they showed you for linear kinematics are true for angular kinematics. And that's fine. Here's the chart that shows you how these things are related. In the linear, well, it doesn't show you how they're related. These are your linear variables, your rotational variables, and their definitions, actually. They're calculus definitions. And here they show the rotational and translational kinematic equations. And then here they show the relationships. They use S instead of X, and that's fine. S being the arc length or the distance along the edge of the circle, and the relationship, which we already talked about. Now there's something up here that I want to talk about, and that is the centripetal acceleration. So we're talking about a lot of different accelerations here. We have the linear acceleration, which is, if you're going in a circle, the linear acceleration is how fast you're speeding up along the edge of the circle, right? So if your rotational speed or your tangential speed along the edge of the circle is increasing, then you have some kind of a linear acceleration along the edge of the circle, or tangential acceleration. And that would still be called A or A sub t for tangential. But when it's A sub c, don't confuse this with tangential acceleration. This is still centripetal acceleration, which means the acceleration that holds this thing in the circle. So this is still the acceleration towards the center of the circle, which actually causes this thing to turn. So that's your centripetal acceleration. If you have both centripetal and tangential acceleration, so that you're going in a circle, the centripetal acceleration keeps you going around and around, but the tangential acceleration is speeding you up in your path along the circle, then you have to add those two accelerations together to get the total acceleration. The total acceleration in that case, if you add one that's pointing in and one that's pointing this way, will be actually off in this direction somewhere. So we'll have a kind of a funky acceleration in the end. But you will have to add those two together, because going in a circle always implies you have centripetal acceleration that keeps you in the circle, whereas the tangential acceleration is one that gives you motion, more increased circular motion, I guess. So here they're talking about a centrifuge, which is the little machine that spins little bottles of chemicals around to separate your precipitate from your solution or whatever. And so this centrifuge has a radius of 20 centimeters and accelerates from a maximum rotation rate of 10,000 RPM to rest in 30 seconds under constant angular acceleration. So it has an angular acceleration, but there's also a centripetal acceleration on the bottles in the centrifuge. I really want to get a big centrifuge that does big bottles of stuff. Because with a big centrifuge, you can make tomato juice that's clear. You can make like clear tomato soup, and it really tastes like tomato soup. It's kind of amazing. But you can see through it. It looks like kind of like reddish water, pinkish water. But I want to do that. Anyway. So they want to know what is it's rotating clockwise. What's the magnitude of the total acceleration of a point at the tip of the centrifuge at t equals 29 seconds? What's the direction of the total acceleration vector? Okay. So what they've given us here, and they've given us a lot of words here, but what we really need to do is we need to assign a variable name to each one of these things according to the standard kind of variable name. So the radius, of course, is r. Maximum rotation rate, it's accelerating from the maximum rotation rate to rest. So this is our initial. Our initial rotation rate is 10,000 RPM. So that's going to be our omega initial, just omega. Omega is 10,000 RPM. Sorry, omega 0 is our initial momentum. So omega 0 is 10,000 RPM. When you go to rest, of course, that's omega of 0, so our omega final is omega equals 0. So we're just labeling these things to start with. And then 30 seconds, of course, is our time. And we know that is a constant acceleration, but we don't know what that is. We want to calculate that constant angular acceleration. And we want to know we want to calculate the total acceleration, which would be the constant acceleration, angular acceleration, plus the centripetal acceleration, which would be the total acceleration. And then they want to know what is it at 29 seconds. So they've given us a different time to do another calculation. So we just need to label those things. I don't like that they don't label them. They should just have a list of all the things that are in here so that we don't forget them, we don't mix them up. But anyway, they should. So once we do that, they calculate the acceleration by simply taking the difference in the omegas and dividing by t. Remember that the omega 10,000 RPM needs to be converted, which they do right here. 2 pi divided by 60 is the conversion for radians per second. And then, of course, the original one is 0. That doesn't have to be converted at all. And then in 30 seconds, and because it's constant, you get a negative 34.9 radians per second squared of angular acceleration. So that is our angular acceleration. What is the tangential acceleration going to be? So back here, if you notice, when they added the accelerations, they don't add the angular acceleration and the centripetal acceleration. You can't add angular things to linear things. You can only add linear things. So what they're going to do now is they're going to convert the angular acceleration into a tangential acceleration so that they can add it to centripetal acceleration. So to convert to tangential acceleration, what do? Well, you divide by r to go to angular, you multiply by r to go to linear. We have our angular, so we multiply it by the r to get the tangential, and here it is, negative 7.0 meters per second squared. There's our tangential acceleration. They also are going to, they also want to calculate, let's see here, the total acceleration at t equals 29 seconds. So what we're going to do is we're going to now calculate the final angular velocity at 29 seconds using the kinematic equation. We know our initial is 10 to the fourth, 1 times 10 to the fourth. Make the conversion again. We know that our angular acceleration is negative 34.9, and the time is now going to be 29 seconds. So then we calculate our final angular velocity at 1,047.2 radians per second. Why do we need to know that? Because we need to know the angular velocity to find the tangential velocity, and we need to know the tangential velocity to find the centripetal acceleration. Because the centripetal acceleration depends on how fast it's moving at that moment. So at that moment, we convert from angular velocity to tangential velocity using r, and you're getting 7 meters per second of tangential velocity. Then we calculate the centripetal acceleration, tangential velocity squared over r, 245.0 meters per second squared. Now we have the acceleration tangentially, the acceleration centripetally, and the acceleration tangentially. These two things added together are going to give us our overall acceleration. But you have to remember that these two things are both vectors, and they are 90 degrees to each other. So they're going to add like vectors. We cannot just add these two numbers together. We have to add them using the Pythagorean theorem. So we use the Pythagorean theorem to add them together. We get an overall acceleration magnitude of 245.1 meters per second squared. And then we calculate the angle by taking the negative 7 over the 245 to get an angle of negative 1.6. To show that, the tangential acceleration is this way, the centripetal acceleration is towards the center of the circle, and the overall acceleration is slightly forward of the centripetal acceleration, which means that it's moving slightly, the acceleration is slightly tipped in this direction, which would make sense since this is the direction of motion, and it's slowing it down. Right? So it seems complicated. These kinds of problems seem complicated. There's lots of equations, lots of back and forth, but really the key is to write down what they've told you and label it with the proper variable name, whether it be linear variable names or angular variable names. Write everything down and see what you've got to start with. And then I would recommend taking whatever one you have the most of, linear or angular, and go with that. If you have mostly linear variables they've given you, then use linear kinematics to solve the problem and then convert if you have to. If they're wanting you, if you have mostly linear variables and they want to know the angular acceleration, we'll solve the problem using linear variables and then convert the linear acceleration to angular acceleration at the end. Or vice versa. I probably should point this camera at me while I'm teaching that. Anyway. Of course, I had a camera on the computer I could point to too. Okay, so moving on to 10.4. Moment of inertia and rotational kinetic energy. Have we talked about moment of inertia yet? We haven't, right? That was the other class. Okay, so what about kinetic energy? Is there a rotational kinetic energy? And the short answer is yes. The long answer is this. Kinetic energy equals 1/2 mv squared. And this would be the, if you replace that v with the tangential velocity along the edge of a circle, which I don't have a picture of. But anyway, if you're moving along the edge of a circle, the kinetic energy is 1/2 mv tangential squared. Your tangential velocity along the edge of the circle. But that tangential velocity, of course, is equal to the angular velocity times r. So then we replace the velocity tangential in the equation with omega times r. And of course, both of those are going to be squared, so you're going to have mr squared omega squared. Well, this looks just like kinetic energy in rotational terms if you group the m and the r squared together and call that like your mass thing. Well, okay, sure. So this is 1/2 times some mass thing times omega squared, right? So why would the r squared be grouped together with the mass? Why does it matter? Well, the simple answer is this. When you're rotating something, the mass is important. Something that is more massive is harder to rotate, right? We've experienced that before. For example, you can really tell the difference between a very, very heavy, massive door and a very lightweight door when you open it. You really can. It's a big difference. However, where the mass is also matters, right? Well, what do you mean, where the mass is? Well, imagine you're lifting up something very, very heavy. Let's say you're lifting up a car, and you're using a lever to do it. In other words, you're rotating the car. Instead of lifting it straight up, you're rotating a lever to lift up the car, okay? If you put the car the long, long distance from where you're holding the lever and very close to the fulcrum, then it's much easier to lift the car. That's the whole idea of a lever, right? What it looks like is this. So if you have your car here, and you put your lever under it here, and here's your fulcrum, and you pull on this end, and your mass is way over here, it's actually really easy to lift that car. In fact, even if you don't have a fulcrum, even if the mass is not on the other side of the fulcrum, because some people would say, well, that's because of You know, the whole fulcrum thing. What if you just have a long stick and you put a mass on it like this? And this is just sitting on the ground, so the fulcrum is on this, or the mass is, and the force lifting the mass are on the same side of the fulcrum. And you just lift right here. Well, because the mass is so far away, or on this one side of this rotating thing, this rotating fulcrum, or rotating lever, it's actually easier to lift this thing. But if you put the same mass out here, holy crap, that makes a difference. The idea of this is that where the mass is matters when it comes to rotation. In linear motion, it doesn't really matter that much. In linear motion, it doesn't matter if the mass is in the front of the car, the back of the car, the top of the car, the bottom of the car, spread around all around the car. It doesn't really matter. It's just mass and you're just pushing it, right? But in rotation, it really matters where it is. Going back to this equation, m times r squared, well, r is the radius of the circle, and the mass that we care about is on the edge of that circle. So if the r is further away, then this number here gets bigger. It's like this mass thing gets bigger. Well, is that true? Yes, we just showed that that was true. We just showed that if you have something that's further away on the stick from you, if it's further away from the fulcrum on the stick, I guess, and you're lifting it, then you have this, it's kind of a harder thing to lift. If it's closer to your fulcrum, then it's an easier thing to lift. It changes the amount of energy required to lift it, right? So it certainly is the case. We call this thing right here, this mr squared, we give it a name and we call it the rotational inertia, or sometimes often called the moment of inertia. So it's either called just the moment, or the moment of inertia, or the rotational inertia. And the rotational inertia depends on not only what mass is in the problem, but where the mass is relative to the rotational point, where the point where you're rotating around. Now, it actually doesn't have to be relative to the rotational point. It can be relative to any point you want, as long as you use that same point in your math throughout the entire problem that you're doing. It doesn't really matter what point you measure it from. So this moment of inertia thing is really kind of, the R is, it's a, well, you can choose the size of it, but the relative size of I, or the relative size of this moment, will be the real determining factor. It's kind of like choosing where your 0 point is for your gravitational potential energy. In fact, it's exactly the same. It's almost exactly analogous to that, mathematically speaking. So anyway, so how are we going to use this? Well, we've just calculated the kinetic energy, or figured out the kinetic energy of a point mass going around the edge of a circle. And that's fine for some things, like a ball. If you're swinging a ball around your head on a string, that's kind of like a point mass on the end of a circle. If a car is driving around and around in circles, that's kind of like a point mass. Car is not exactly a point mass, so it's not a perfect situation, but it's, kind of like that. Of course, planets going around other planets, it's a pretty good analogy, and things, like that. But what if it's not something that's kind of like that? What if it's a stick spinning around its center? Well, a stick is nothing like a point on a ball on a string, because a stick has its mass distributed. Some of it's close to the center of rotation, and some of it's far from the center of rotation. What if you're spinning a bicycle? Or you're spinning a rhubarb, something that has some weird shape to it, that where the mass is not distributed evenly. Some of it's close, some of it's far. Who knows? It's in the real world, things don't rotate in this nice point on the end of a string kind of thing. Things have a tendency to rotate in more crazy ways in real life. But we'll get on to that in a minute. Let's say that let's start with, instead of one point on the end of a string, let's do many points on the end of many strings, because that will help us to figure this out a little bit. If we had many points, we'd have to add up all their kinetic energies using a summation like this, right? And of course, with a summation, constants come through the summation because they don't change as you add them together. So we can pull the 1/2 out of this summation. But the masses may be all different, and the distances to those masses could all be different, and even their angular velocities could all be different. What if their angular velocities are all the same? Let's say that it's many objects, and maybe on many strings and many different lengths and many different masses, but they're all going the same angular velocity. Well, then that can be pulled out of the summation. So outside the summation, you have a 1/2 and an omega squared, and inside the summation, you're adding up a bunch of little masses on strings. Well, hopefully you know where this is getting to. You can treat any object as a bunch of little masses on strings if you can figure out where those masses are and how much they weigh. Right? Let's say you have this object here. Here's a funny shaped object. If I'm spinning this object here, this drill, right, and I'm spinning it around this point right here so that it's doing this. Well, all I do is I can make this my 0 point and measure out to every little point on this drill and assign every little point an R and figure out how much mass is at each one of those little points. And then I can calculate the moment of inertia of this thing. Now, it would be painstaking, difficult, and nearly impossible to do, but if I could do it, theoretically, we could calculate the rotational kinetic energy of this thing spinning around on this thing, and it would be fine. We would have that moment of inertia. Well, we also know that summations can be turned into integrals. So if you had a function that drew the shape of this thing on a piece of paper, if you could write a mathematical function that drew an outline of this thing, of course it wouldn't be a function, but anyway, we could have a series of functions. Anyway, the point being is that if we can map out this shape and where the masses are in a function of x and y, then we can plug that into an integral and integrate it and figure out the moment of inertia of this thing. Turns out it's much easier to just spin it and see what happens and then measure the moment of inertia. But, we're into the theoretical things. We're doing theoretical stuff. In the end, what we discover is that no matter how we calculate the moment of inertia of an object, the kinetic energy is going to equal 1/2 times that moment of inertia times the rotational velocity squared. So you can calculate the kinetic energy of this thing. I've not seen this picture before. This is new. So there's this idea that has been, this is a long-held idea. In fact, the first time somebody did this, I think, was over 100 years ago. But if you can have kinetic energy in a spinning object, then you could use that kinetic energy to spin other objects or to move other objects. And so what people thought was, well, what if we put an object inside of a car that has a very, very high moment of inertia, which means it can store a lot of kinetic energy when you get it spinning really fast, right? If that I is really big, then 1/2 I omega squared will get really big once you start spinning it super fast. So they make a wheel called a flywheel. And a flywheel is essentially like a wheel on a bicycle. It has spokes going out to the outside. And then on the outside, they put some really heavy material like lead on the outside, because that's very far away from the center, so it's going to make the highest moment of inertia possible once you spin it, right? And then you start spinning that wheel super fast. Like you put it inside of a car, for example, and you spin it really, really fast before you start going in the car anymore. So you get that thing spinning like 10,000, 20,000 RPM, some super fast, like crazy speed. And then when you want to start the car, you go ahead and tap into that energy. You could, in this case right here, it looks like they've got a spinning wheel probably inside of here, and it probably is connected to a generator, like an electrical generator. And then as that thing, as they engage the electrical generator, there's a switch that turns that generator on and connects it. Then it would charge a battery or power the electrical motors in the car or whatever. And then you could start moving in this car from this spinning, super fast spinning wheel, right? Now, what's the downside of it? It turns out that at the speeds that we like to travel and the amount of stuff we like to take with us when we travel, the wheel has to have an incredibly high moment of inertia, and it has to move incredibly fast. And so what that really means is the wheel needs to be quite large. So automobiles that would use something like this as their energy source would have to have a huge amount of space taken up by the spinning wheel. Also, moving parts have a tendency to wear down. So if you have a spinning wheel, it's got moving parts, it has ball bearings and other things like this, it's going to have this tendency to wear down. The new idea is that we use no ball bearings. We use a floating wheel, and the floating wheel would be floating by magnetism, and that actually has real potential, very real potential for the future. So anyway. So here's an example where we're going to take the moment of inertia of a system of particles. Instead of one particle, it's 6 particles on either side of the axis at different distances. And so what they do is they take the moment of inertia of each one and add them together, all together, to get the total moment of inertia. And then you can calculate the total kinetic energy. And it turns out that you can do this for different shapes of objects using calculus, and this is the result right here. These are the results of the different moments of inertia of different shapes rotating around different axes. We'll do an example of this when we get back, when we come back tomorrow. We'll do an example of calculating the moment of inertia of a particular shape so that you can see how that's done. And we'll leave it at that for now. And we will see you tomorrow.